Yes, Dr. Praveen, how are you?
I'm doing good, thank you.
Yeah.
I think today with us, Professor Subramaniam is also there. He joins.
Yeah.
Thank you, sir, for joining and taking your busiest time to us. I think you're on mute, sir.
Yes.
Yes, yes.
Okay.
How are you doing, sir?
Excellent. Thank you.
Thank
Of course,
you so.
it is morning for me.
Okay, it's morning for you. Okay, great. So just in 2 to 3 minutes, we will be starting the program, sir.
Sorry?
I said in 2 to 3 minutes, we will be starting the program.
No problem.
Okay. Lakshmi, is it all set?
Yes, sir. All set. We can start the event.
Okay. So please start the recording and then please proceed.
Yes, sir. Recording has been started.
Okay.
A very good evening to everyone. My name is
evening.
Lakshmi Sri, pursuing master's degree at IIT Hyderabad. I feel honored to extend my warm welcome to all the people present here. On behalf of IIT Hyderabad student chapter at Earthquake Engineering Research Center, I want to take this opportunity to welcome our honorable guest, all the faculties, industry people, participants from the academia, research fraternity, and all the students to join the webinar on an advanced topic, Probabilistic Framework for Seismic Vulnerability Assessment of Aging Infrastructure Systems. Today, we have the privilege to have with us an expert in the field of structural earthquake engineering who shall be reflecting on the theme of this webinar. Now, I would like to introduce our keynote speaker for the day, Dr. Shivang Shekhar, to our esteemed audience. Dr. Shivang is currently working as an assistant professor in the School of Civil and Environmental Engineering at IIT Mandi. Before joining IIT Mandi, he also worked at BITS Pilani. He did his MTech and PhD from IIT Roorkee and IIT Bombay, respectively. For his doctoral work, he received the Excellence in PhD Research Award, Best Thesis Award from IIT Bombay in the year 2020. Recently, Dr. Shivang is also selected for the Promising Young Structural Engineer Award in the year 2022 from the iStructy team. Dr. Shivang is also serving as an early career editorial board member for the prestigious ASCE ASME Journal of Risk and Uncertainty in Engineering Systems. Prior to joining academia, he has 3 years of industrial experience in a structural design consultancy firm. His research interests include structural reliability, seismic vulnerability, and loss assessment of bridges. He also works on non-linear modeling and analysis of structures, probabilistic seismic risk, life cycle analysis, application of advanced machine learning algorithms for multi-dimensional fertility models, and uncertainty quantification in structural reliability problems. Presently, Dr. Shivang is working on developing a framework for identifying optimal retrofit techniques for older bridges located in high seismic zones of India. Okay, this is a brief introduction of our keynote speaker, Dr. Shivang Shekhar. Now, before we start the event, a small announcement to all the participants. If you have any questions, doubts, or clarifications, please do type your queries in the chat box only. We will have sufficient time for the discussion at the end, where Dr. P. Praveen Kumar Venkatrao, Faculty Advisor of Student Chapter, will be the moderator. Now, without any further delay, we will turn the time over to Dr. Shivang. Sir, over to you, sir.
Yes, thank you, Lakshmi, for a nice introduction. I will just share my screen.
Yes.
Is my screen visible now?
Yes, it is visible.
Okay, thank you. Yes, thank you, Praveen, for the invitation, and Lakshmi for the nice introduction, and obviously Dr. Subramaniam, thanks for coming for this talk.
You're welcome.
Okay, yeah. So without any delay, I will start my talk. So mostly, I will talk about like we have aging infrastructure systems like bridges and all, which are built long time back, like in the years 1970s, 80s, and all. So how to basically assess the vulnerability of this infrastructure system, which are not only getting aged with time, but also when it is located in high seismic zones like zone 4 and 5, it is susceptible to earthquake, high intensity earthquake also. Okay, so I will just start my introduction. So we all know that bridges are lifeline infrastructure system. They act as a key element during the in the road transportation system, and however, these bridges are mostly located in very like exposed like in located in harsh environmental exposure conditions, like when it is located close to sea or obviously marine. Atmospheric is also is very high environmental stressors that leads to the basically the corrosion of the or the degradation of the material of the bridge components. Okay. Now, in addition to that, as I said, we are looking into the older aged highway bridges. These are also designed with antiquated design standards. Okay. So we have seen like these are some of the few examples of the bridge failure across the globe where the corrosion leads to the reduced structural capacity and all. Now, what basically the corrosion does, what is the long-term impact of corrosion? We can see from this basically kind of a figure that the corrosion leads to the deterioration of the structure. That basically leads to the reduced service life. Okay, so there is a need for an repair and retrofit of the structures. However, when these structures are in addition to that, basically these structures when these are located in high seismic zones, they are vulnerable to other natural hazards like an earthquake, and which leads to the which may lead to the failure of the structure. So there is a need for a repair and retrofit program, and also these repair and retrofit programs should be adequately managed because we know that we are constricted with the economic resources. So there is a need to develop a tool that takes into consideration of like whatever the existing infrastructure system, how to assess its vulnerability, what are the losses if it fails during its service life and all. So there are some more figures related to corrosion. We have I've talked about that corrosion leads to the loss in structural capacity of the bridge components and members. So if you see related to India, in India, like, this is a very little bit old data of 2011. So we can see that out of 14,005 to be in very structurally deficient condition, and over 2,000 bridges are very old and weak and thereby demanding reconstruction. If we move towards US, as we know, US is a developed country. These bridges, more bridges are basically built in the year 1970s or 80s or maybe 1990, around that time. So we can see 39.1% of these bridges were found structurally deficient. This is as per 2017 AC report. If you see 2021 AC report, this percentage will be a little bit higher. Now, FHWA, the Federal Highway Agency of US, they say that $123 billion is basically required to eliminate the structurally deficient bridges. And then there are some more data related to, I guess, UK and all. And some people also say that corrosion cost average of 3% of the world GDP. Okay, so as I said, these infrastructure are basically degrading when they are located in harsh environmental stressors conditions. So degrading, the structural capacity gets degraded, and when an earthquake or natural hazard like an earthquake comes, there is a chances of collapse and failure of this infrastructure system. So there is a need for an early repair and retrofit program. Okay, so that's the thing I was talking about here, that failure leads to the loss of functionality, and therefore there is a need to assess the vulnerability of the existing highway bridges. So typically, I was told by Praveen that in this talk, mostly the participants are students. I will try to keep my presentation a little bit simpler so that at least students takes away some of the key aspects related to the structural and earthquake engineering and specifically this research area. So basically, we come for a structure which is located in a seismic zone. What we do is that we can, for the existing structure, we can assess its vulnerability by developing seismic fragility curve. So seismic fragility curve basically gives the probability of failure for a given intensity capacity measure. So if my intensity is 0.4 G, what is the probability of failure it gives? So basically it gives if the demand is greater than capacity, for a particular PGA, what is the probability of failure? So there are different methods to develop this seismic fragility curves, starting from the expert-based judgment method, your empirical-based method, your experimental-based method. But with the advent of computer programming and sophisticated computers and all, people are moving towards analytical method for where obviously we take some help from the experimental result, because experimental result always serve as a base for validating our numerical model. So we go for analytical computer-based simulation and develop seismic fragility curve. So these are basically, I am showing for a suppose as-built bridge. If the bridge is getting degrading, means column is getting degrading, there is a corrosion. The bearings are getting frozen and locked due to corrosion of the steel bearings. The girders are also getting degradation. Then obviously it's the fragility or the probability of failure will increase. Okay. So my talk in today's presentation basically will cover 3 points. First, I will talk little bit basics of corrosion, why we need to model the probabilistic modeling of corrosion deterioration, because there is lots of uncertainties there. Why we are looking for towards the probabilistic modeling of corrosion, then how to develop the time-dependent seismic fragility curves, and then if you are developing time-dependent seismic fragility curve for a particular bridge, what are its limitations, and why we have to go for a multi-dimensional or parameterized seismic fragility curves if you are looking for a vulnerability assessment for a class of a bridge, not a single bridge, for a class of a bridge. So I will just talk about these 3 topics one by one, and then at the end I will conclude. So let's start with the first topic of corrosion. Okay. So we know that when a bridge is located or any reinforced concrete or steel structure basically located in a adverse atmospheric condition, like located close to the sea and all, there is a chances of corrosion. Like if there is a steel structure, the girder gets corroded. If it is a bridge pier, the bridge pier also gets corroded. And if it is the bearings, like steel bearings, the steel bearing also gets corroded. There is a locking of roller bearing due to the accumulation of rust and debris. Even if it is an elastomeric bearing, these bearings also gets aged with time. Okay, so we'll first look into the reinforced concrete bridge piers, or we can call as a bridge columns. So in the bridge columns, we know the bridge column, basically the lateral load carrying capacity of a bridge depends on the bridge column. So we will first look into the bridge columns. So I have just taken a bridge column, and then I'm just trying to show you that due to the ingress of the chloride ion, if there is a chloride induced corrosion due to high amount of chloride content, due to the ingress of the chloride ion, there is a corrosion of reinforcement. So what happens? So I'm not going to explain the process of corrosion. We all as a student have learned that, but there some kind of chemical process occurs that leads to the formation of rust. This rust basically occupy larger volume than the sheets. That leads to the expansion, then cracking and spalling of the concrete. So these are some of the local damage in RC structure, like spalling of concrete, your confinement, your reinforcement that is basically used to confine your reinforced concrete column, or basically your longitudinal reinforcement also buckles due to corrosion. Due to corrosion, there is a cracking in the rebar, and obviously at the end the concrete spall. So we can see there is a corrosion of the longitudinal reinforcement. So this corrosion is basically a multi-stage deterioration process. So multi-stage deterioration, it doesn't start at the day one when you construct your reinforced concrete member. It starts after some time. Okay, so when your chloride, if there is a chloride environment, or when the CO2 penetrates, after some time, when it reaches the critical chloride concentration, then the corrosion initiates. So you can see it here. I have just tried to show it here that after some time the corrosion initiates. Once the corrosion initiates, you can see there here I am showing the initiation time. So there is an expansion. So the rust forms and there is an expansion. So that leads to the cracking in the concrete. And then with this, the extent of the corrosion gets increased. So stage 1, stage 2, stage 3, and stage 4. So there are 4 stages of corrosion. First is your time till the initiation. Then from initiation time till the rust expansion and the cracking of the concrete occur. And then the spalling of the concrete. In terms of resistance, if you want to see it, you can see it here. In resistance is 100%, and once the corrosion starts, it basically starts to degrade, cracking of concrete, then spalling of concrete. So basically 3 time instant we have: T time to initiation of the corrosion, T critical, time of cracking, and then time of spalling of concrete. So your 4 multi-stage deterioration process is basically defined as diffusion of chloride or CO2 in the concrete, then corrosion propagation, crack formation, and your cracking and spalling of the concrete. Okay, so when the chloride ion diffuse, when the surface chloride concentration reaches the critical chloride concentration, then only the corrosion initiates. Okay, so that leads to the formation of the rust product. Remember, this reinforced concrete member has some kind of protective film. Okay, this protective layer, basically, the more the cover depth, the lesser the kind of water cement ratio. There's several chemical characteristics that basically delays the corrosion initiation. So if you see just the concrete cover depth, the larger is the concrete cover depth, the corrosion will basically delay it further. Okay. Now there are some researchers, we should be thankful for these researchers and all. They develop mathematical model for finding the initiation time of corrosion, and basically this depends on your fixed second laws of diffusion. And when we solve this differential equation by applying some kind of boundary condition and all, then there are several literatures available that basically gives, based on the several parameters, what will be the initiation time. So if you see this equation, this is very much used in the literature to assess the corrosion initiation time for reinforced concrete member. We can see that it depends on surface chloride concentration, it depends on a critical chloride concentration, and it depends on your cover depth. What is the concrete cover depth? So larger is the concrete cover depth, the more is the initiation time, the lesser will be the corrosion, you can say, if you take a service line. So, and it also depends on several environmental factors. Basically, these equations are basically developed based on the lab tests and all. So they put some of kind of a environmental correction factor like Ke, Kc, and Kt, and obviously this is the diffusion coefficient. Basically, the higher the diffusion coefficient, the earlier is the initiation time of the corrosion. So in this document, and obviously there are several other researchers have also who works directly on the corrosion based on the exposure scenario, like your atmospheric, marine splash, or tidal or submerged zone. They have given the parameters for this. Okay, like what will be K, Kc, Kt, your diffusion coefficient, what is your surface chloride concentration, critical chloride concentration, depend on the grade of concrete and the age of concrete. Okay, now again, you can see in this table here, and that's why I am saying that we should do a probabilistic assessment, because there is no fixed number. So you can see it here. They have, for each thing, they have given a mean and a standard deviation. Basically, they have given a distribution, a normal distribution or gamma distribution for different parameters. Okay, so this parameter should be used in a probabilistic Monte Carlo kind of simulation by taking the uncertainty to estimate the corrosion initiation time for a reinforced concrete members. Okay, so what we basically do in our work is that, like, suppose I have taken a reinforced concrete member, like a reinforced concrete column with a cover of 1.5 inch, that is 38.1 mm. I have assumed a water cement ratio of 0.5 and say that this is located in marine splash exposure and all. And then taking uncertainty of these parameters. Uncertainty of parameters are basically mentioned in this table, and then taking uncertainty in this parameters and do a Monte Carlo simulation. Means we generate random samples of all these parameters, and then based on this we estimate the initiation time. Since we have random parameters, we are doing Monte Carlo simulation, we will get a histogram, and on that histogram we can fit a distribution. Okay, so you can see it here, like based on the uncertainty of the parameters and considering this fixed cover depth and water cement ratio, we can get a mean initiation. We are getting a mean initiation time. Generally, for the whatever the numbers are getting generated from Monte Carlo simulations, we fit a distribution, and here we are getting a log or normal distribution with a mean initiation times of 10 years, and obviously there is a kind of deviation or coefficient of variation. Now this is your first stage. First stage is your diffusion. We try to find what will be the initiation time for the corrosion of reinforced concrete member based on the structural characteristic of the member. Next stage is your corrosion propagation phase. Once it diffuses, the chloride and iron penetrates and the rust starts forming. Okay, the rust, the amount of rust basically that forms depends on what is the corrosion current density, or what is the corrosion rate. The higher the corrosion rate, the more is the the more is the rust formation, or the higher is the sectional area loss of the reinforced concrete member. So again, here again, we went to the some of the literatures that is available in some of the renowned journals. journals, and we have seen that your corrosion rate, because basically some researchers says that it is a constant value, some researchers that it is a time independent, some researchers says it is a time dependent. And like the document that I was talking about, the Durakri document, they based on exposure class also, they also again gives the corrosion rate with standard deviation. Again, here uncertainty, we cannot work with a single number. So we have to take the uncertainty and then based on this try to find the area loss. There are some more, you can see this is again from very good literature. I try to just show it here. There are different models available in the literature that try to model the corrosion rate. Okay, so corrosion rate depends on several factors like water cement ratio, what is the chloride concentration, cement content, and several models are available. And these researchers have also tried to, like, this is basically a summary of that, how the corrosion rate varies with time and all. Some people say it's constant, some it says that it degrades with time, some it says with increase with time. But the most widely used in the literature is the Wu and Stewart model. So that gives you the initiation corrosion rate, and then it says that it decreases with time. Now, I will little bit go again to the second stage of the corrosion, the cracking of concrete. Okay, so when the concrete will crack, so there are again some of the models that are available in the literature that talks about the formulations for to calculate the cracking of the concrete. And then in addition to that, once the crack formation, there are some of the more literature that gives you the formulation how the spalling of concrete occur, at what time it occurs. If we know the corrosion rate, amount of rust forms and all that, basically help us to calculate the time when the spalling of concrete occurs and all. Now, we have seen little bit on what is corrosion, what is the mechanism of corrosion, basically chloride induced and carbonation induced corrosion, that basically tells about when the initiation occurs, then cracking, spalling of the concrete. Now, what are the effects of the corrosion? So one of the fundamental effects of the corrosion is a reduction of the cross-sectional area or the mass loss of the rebar, reinforcement and rebar. You can see I have shown that this is a corroded rebar. Now, in case of chloride-induced corrosion, due to the spatially variability of the chloride ion, there is a corrosion called as pitting corrosion. So across the length of the rebar, the corrosion is not uniform. There is a non-uniform corrosion. So at different location, different pits forms across the length of the rebar. So that's also basically leads to the reduction, obviously, in cross-sectional area. And there are several other secondary effects also for corrosion, like obviously when the volume, the cross-sectional area reduces, basically the rust is forming, that expands, that leads to cracking of the cover concrete. So there is a bond strength reduction, there is a compressive strength of the cover concrete also gets reduced. Then there is a change in the stress and strain of the reinforcement. So there are different effects of this corrosion. Now, I was talking about that corrosion, like basically the chloride-induced corrosion not only leads to the area loss, but this area loss is very non-uniform across the length of the rebar. So we have seen that people like generally when we model the cross-sectional area loss in the chloride environment for a beam or a column, we just take a uniform area loss. But the experimental results in the past or the real world field scenario also says that this corrosion is not uniform. There's a small pits form across the length of the rebar. Okay, so we can see some of the figures that these are the small pits form across the length of the rebar. So one of the most widely used models for the cross-sectional loss of a rebar in chloride environment is basically hemispherical kind of a shape. So you can see that there is a uniform area loss, and then at some location there is a pits are formed. So this is a cross section. If we see across the height of the rebar, this is just a representation purpose and all. So you can see uniform area loss is there, and at different location pits are basically formed. Pits are forming means much more area loss, like these kinds of pits are basically forming. So people idealize this pits as a hemispherical shape and all. Work done by Weil and Stewart, basically they have done this kind of test in a chloride, experimental test in a chloride environment, and then try to model this. So there are some equations given, basically how to get this area loss at basically this cross section. So this A is basically uniform cross section, and if we take area loss at section BB, you can see uniform area loss, and in addition to that there is a dip pit. So some formulations are available in the literature which can be used to calculate this area loss again. Now again, you can see that for representation purpose, I have also shown here. Here the pit depth is very less. Here it is little larger. Here pit depth is slightly more larger. Again, it is more larger. It is lesser. So this is non-uniform. Across the length of the rebar, these pit depths are not uniform. Basically, it is non-uniform. So how to basically take this pitting factor like across the length of the rebar? So again, what we do in our work is that we take from the help from the experimental result carried by some of the researchers like Stewart and all, and then we have seen that, is I'm audible in issue?
No, it is absolutely audible, Shivang. You can continue. Yeah.
So what he does is that he take a 100 mm rebar and then do an accelerated corrosion test kind of, and then measure the pitting factor at different location across the length of the rebar. And then based on this, he suggested a distribution. Again, why distribution? Because there is an uncertainty. So he suggested a distribution for the pitting factor. Specifically here, it is a Gumbel extreme value kind of distribution is there. So we have taken the same bridge column and then try to plot this is again showing the mean area loss. We try to plot if there is a uniform corrosion or if there is a pitting corrosion, how much will be the area loss across the service life of the bridge. So we have considered for an example here 100 years as the service loss, then how much will be the area loss. Now, in addition to that area loss, I have already said that this pitting corrosion also leads to the secondary effects of corrosion, like your reduction in the or spalling of the concrete or reduction in the cover strength of the concrete. The reinforcement corrosion of the ties also leads to the reduction in the confinement. So that also happens, the spalling of concrete and all. So there's different secondary effect. Also, due to non-uniform reduction in the cross-sectional area, steel mechanical properties like strength and ductility also gets reduced. So we have also tried to look into the literature and then try to see how people have try to model this based on the percentage mass loss of steel. So these are some of the equations that can be used to see the secondary effects of the corrosion. And then we try to plot it like how across the service life of the bridge, how much will be the degradation or the loss in the concrete cover strength, loss in the ductility, steel ductility, loss in the longitudinal steel strength and all. Now we have seen the corrosion of bridge piers. Now next little bit see on the corrosion of bearings. Again here for the example here I am only showing the steel bearings. Which basically nowadays if you see are not used at all except the railway bridges, the truss bridge and all. But for the older bridges like Indian code most MOST also says that there are steel rocker and roller bearings are basically used for bridges. So these bearings also gets corroded. So basically what happened is that these bearings are basically fixed through an anchor bolt in the pedestal on the top of the bridge column. So these anchor bolts due to two different environment. You can see half of the anchor bolt is in the atmosphere, half of the anchor bolt is in the pedestal, which is in reinforced concrete. So due to these two different dissimilar environment, there is a necking kind of action form. Again, these are all taken from the past experimental result, past field observation test across the globe and all. And we have seen that like people say that this anchor bolt specifically fails due to two dissimilar environment. There is a necking. So once there is a necking in the anchor bolt, the lateral load carrying capacity of this bearing basically gets reduced. In addition to that, due to the accumulation, because these bearings are made of steel, so it basically corrodes. The exposed steel member also corrodes. So this exposed steel member corrodes, rust forms. So if we have a roller bearing, this roller bearing has an action of rolling, like basically it has a rolling kind of action, but this due to accumulation of rust and debris, this basically leads to the frozen and locked bearing. So the deck which is allowed to move due to the horizontal forces of the vehicle and all are basically not moving, and extra forces are basically getting transferred to the bridge column. So you can see some of the figures that basically talks about the frozen and the locked bearings. So what it does, there is an increase in the coefficient of friction. So the roller which is basically which has to roll due to the higher coefficient of friction, due to the corrosion, it cannot roll. Now we have seen some of the effects of the corrosion of concrete members like bridge columns and also the bearings and all. Now we can see that how if there is an aging bridge, the bridge which is basically gets deteriorated with time, how to develop the time-dependent seismic fragility curves. Okay. So as I said, we have to do a probabilistic simulation. We have to take uncertainty across different parameters. First uncertainty, when we are doing any kind of or developing fragility curves, we have to obviously take ground motion uncertainty. This can be taken based on the site-specific study. We can do a site-specific study and then select the ground motion. Ground motion can be recorded or can be generated. Mostly now, since we have a large amount of database of ground motions, if we know the seismicity of the region, depending on the soil type and all, based on the ground motion prediction equation and all, we can select a suit of the ground motion for the specific region if you want to do a fragility analysis or vulnerability assessment for a bridges in a particular region. So this ground motion uncertainty, basically we have to select a suit of ground motion, not one ground motion. Around 100 ground motion we should select. In addition to that, there is a material uncertainty. As we know, we always design with a characteristic strength. But concrete is an uncertain material. We know that the strength follows a normal distribution and all. Similarly, the steel strength also follows log normal distribution and all. So we have to take material uncertainty also into account. Structural modeling uncertainty. Structural modeling uncertainty in terms of like if you are modeling a full bridge foundation, if you are using substructure approach to model the foundation stiffness and all, the abutment stiffness, the bearing properties, these all are your structural modeling uncertainty. Then there is a deterioration uncertainty. As I said, we cannot work with one single initiation time. We cannot work with one specific corrosion rate and all. We have to take an uncertainty across it. Okay. By combining these all uncertainty, we have to predict the seismic fragility of the bridge of both as built and your deteriorated bridge. So let's see how we do it. Like this is just a graphical animation basically that tries to show that how we are developing your time dependent seismic fragility curve. So the first step is basically we should, based on the regional seismicity, we should select a suit of the ground motion. N number of ground motion based on the regional seismicity we should consider. And then we have to develop the finite element model of the bridge. Okay, so this finite element model is of the bridge should be like a range of bridge models should be developed. Like based on the parameters, we should generate the parameters. And then for each parameter, we should develop N bridge models. Okay, considering your modeling structural parameter uncertainty and deterioration uncertainty. In general, in cloud analysis, what we do, whatever is the number of the ground motion, suppose 100 ground motion we are taking, we generate 100 samples of the bridge by taking uncertainty in modeling parameters, deterioration parameter, and structural modeling parameters. And then these are combined with the ground motion. And then a non-linear time history analysis is basically carried out. And the next is your response of the different bridge components. Remember here we have, it's a full scale bridge we are modeling. So different components are there, your bearings. So basically your columns response can be measured with respect to drift, your ductility can be curvature ductility, can be displacement ductility. Then we have bearing displacements can be measured, your abutments displacements can be measured, your foundation rotation can be measured. So these all response of different bridge components can be measured for each simulation. And then we developed the demands model, which we call as probabilistic seismic demand model. So this analysis we do at different years. Like we know that as built bridge, obviously there is no deterioration. We generate the number of bridge samples considering material uncertainty and structural modeling uncertainty, and then develop a time history analysis. And then based on the result, we develop probabilistic seismic demand model. Similarly, suppose my bridge is at 50 years, based on the deterioration, material uncertainty and other uncertainty, we develop a bridge models subjected to the suit of the ground motion, and again develop the probabilistic seismic demand model. So in the figure here, you can see that PSDM, which we call as, is developed at 0 year, and also at whatever year we are trying to develop fragility curve. Now, once we have the demand model, we have to see the capacity. Again, the capacity is again uncertain. We are saying that, okay, the capacity of bridge piers, suppose, are basically defined with terms of some of the parameters like yielding of reinforcement, or spalling of concrete cover, or complete collapse of the bridge pier, like buckling of the reinforcement and all. Can we give a particular drift for this? No, there is again uncertainty on this. So based on the experimental result, or we can do some kind of a We can develop the bridge model and do it in the software like nonlinear static pushover analysis, and then based on different uncertainty, and then develop the uncertainty around your distribution also, or on the capacity also. Once we have the demand ready and the capacity ready, we can develop the different bridge component fragility curves, okay, at different years. That's why in the figure I say for t is equal to 0 and t is equal to t1. We have the component level fragility curves, which can be combined to get overall like component. When I'm saying component level fragility curves, it's for both your piers, your bearings, your abutments, your foundation. So we can have a demand model for all these components. We can have a capacity model and then compare to get the component fragility curves. And this component capacity is basically combined to get the overall system level fragility curve. Okay. So let's see some small example, just a small example. I'm just trying to highlight how the results looks and all for a kind of a bridge. So you can see it here, a simple multi-span continuous steel girder bridge. The girder is made up of steel, but the bridge pier is your reinforced concrete bridge pier. The bearings are your steel bearings. And we will see, we have assumed that, okay, this bridge is located in marine space kind of exposure condition and all. And then we try to develop the seismic fragility model. So before we go into the seismic fragility model, as we have seen earlier, we have to develop the finite element model of the bridge. So we are doing computer simulation. So we have to develop the finite element model of the bridge. So again, this is some of the work done by me earlier, and some of the past researchers, help from the past researchers helps and all. So you can see I have just tried to show that just in a schematic kind of a representation, how different components of the bridge we can model. Okay, so like we can see the reinforced concrete columns. These reinforced concrete columns basically are modeled using a fiber section approach, a distributed plasticity approach. Like we model a displacement based beam column element, and these elements are basically assigned at a fiber section. Fiber section means we are assigning stress strain curve for this core concrete, for this cover concrete, and then this steel reinforcement, and then this stress strain curve is basically combined to make basically these fibers are basically combined to aggregate a fiber section. So basically non-linearity is captured when you are directly giving the stress strain curve of the material. The non-linearity is basically captured. Then we have your suppose for instance, you can see it here, abutment deck gap. So when there is a this kind of a vibration or the ground moves and all, this decks basically hits the abutment. So some kind of energy is getting dissipated. So this abutment deck gap can be also modeled. The bearings, the roller and the rocker bearings can be also modeled by kind of, we can give a zero length element with the properties, how the lateral load carrying capacity of these bearings are there, we can model. Then we have your abutments can be also modeled by just, we are not modeling the full abutment, but basically the abutment and soil interaction, we are modeling using this kind of a force displacement curve and all taken from the past literature. So again, this there are several literature available, and several textbooks are also available that basically talks about how we can model a full bridge finite element model and all. Now, as I said earlier, that while we are doing the while we are developing seismic fragility curves, we have to see how the capacity of the component basically also get degrades. So what we can do, we can either go into the lab, construct this column for different corroded state, do a reverse kind of cyclic test or monotonic cyclic test, see how the column behaves, develop its force displacement response, and from there obviously we put some strain gauges in the column, see at what drift the reinforcement is yielding, at what drift there is a spalling of concrete cover. So we can basically note this observation from the experiment, but we cannot do everything in the lab because it's costly. So what we can do, we can develop this model in the software. Obviously we have to validate our model. So the good thing nowadays is that I'm just telling this for the students are that there are several experimental database available online for different reinforced concrete components done by the famous researcher across the globe and all. Like reinforced concrete column, there is structural database. For shear wall, there is a structural database. So you can, so suppose if you are trying to develop your model and all, what you can do is that you can take the data from these sources and all, develop that column first, and then try to do this kind of reverse cyclic analysis and see whether your force displacement hysteresis curve is matching with the experiment or not. If it is matching, that means that your model is more or less correct. You are obviously you should not only match one column experimental result, some a set of column experimental results you have to do. Now, once your model is set by matching with this, then you can do for your particular column a kind of a pushover analysis, and then you do a pushover analysis. Here we are doing for different degradation condition. I am just showing you 3 curves, but taking uncertainty, and we do a Monte Carlo kind of a simulation, a range of pushover analysis we do, and then based on this, try to see where at what curvature level or at what drift level the different damage state occurs. So basically these damage states are again defined based on some qualitative kind of description, like your yielding of reinforcement, your spalling of concrete, or your buckling of longitudinal reinforcement, or core concrete crushing. And also they are different based on the past experimental results. You can see that they have defined a drift level and all. So you can, on your experimental result or your computer based experimental result, I can say, you can also do this kind of simulation. Again, I am saying whether whatever you are doing is correct based on whether your model is validated or not. So you have to obviously again and again validate your model. Okay. Now, once we find the capacity of the bridge component, we will do the time history analysis. So this is again just an example for a one ground motion. Again, we have to do a set of simulation. Suppose if we develop the finite element model of the bridge and then do one single time history analysis and try to record the moment curvature response of the call. Okay, so you can see it here. I am just trying to highlight in this plot how degradation leads to increase in demand. So you can see this is pristine, means as built column. And if you are just using the uniform corrosion, means across the length of the rebar, there is a uniform corrosion. You can see there is an increase in drift. But if you do a pitting corrosion, you can see then again there is a if you model pitting corrosion, there is a high increase in drift. If you go for 100 year, so you can see it here, 100-year uniform corrosion. And if you do 100-year pitting corrosion, you can see there is a large increase in drift. Okay. So compared to your as-built case, you can see the degradation case, there is an increase in the curvature demand for the maximum. I'm just trying to show the maximum curvature demand for the bridge component. So this is just show for a one ground motion. In a similar way, we can monitor the response of the bearing. So you can see it here, the bearing response also basically, if you model the corrosion of the bearings and all, the bearings response also gets increased. Now, we have shown you for one ground motion. As I said, to develop the seismic fragility curves, we have to go back to the previous slides, do a set of analysis by taking a suite of ground motion, developing different bridge models, considering the different sources of the uncertainty. And then we have to do the seismic fragility. We have to develop the PSDM capacity model we have developed, then compare demand and capacity model to get the fragility curves of the bridge components. Again, here I'm trying to show just fragility curves of the bridge columns. You can see this is my as-built bridge column fragility curves. If you are using the uniform corrosion only, not pitting corrosion, then the fragility curves coming like this. And if you are modeling the improved deterioration model that considered the pitting corrosion, there is a high increase in fragility. This is again showed for a one damage state. So we can develop for different damage states like slight, moderate, extensive, and complete. And basically these these are just definition. Inside this slight damage state, there is a qualitative description also. Okay, slight, we are saying that okay, yielding of reinforcement is slight damage state. Moderate damage state is spalling of concrete is moderate damage state. Then complete damage state is either rebar buckling or your core concrete crushing. So basically complete damage state. Once we develop the fragility curves for different bridge components, this can be combined to get the system level fragility curve. Okay. Now you can see that for a particular bridge, we know the bridge geometry, we develop its finite element model and assess the degradation condition, and then based on that we do a set of analysis at different years, 25, 50, 75 years, considering corrosion deterioration on the bridge. We are developing fragility curves. So lots of finite element simulation we have to do, and the modeling of the pitting corrosion is also very complex and challenging and computational expensive. So this unidimensional, I'm saying this unidimensional means this fragility curves, whatever we are developing, you can see this is particular for a particular bridge geometry, particular deterioration condition by taking uncertainty and all, and we get one set of fragility curve. if there is a change in the bridge geometry. So I am saying that this is my road transportation network. One bridge I have taken and then develop its fragility curve. If we have to develop the fragility curves for all the bridges in the road transportation network, having different same classification. When I'm saying same classification, generally if we can see the bridges which are regular ordinary bridges. I'm not talking about cable stayed or suspension bridges and all. I'm talking about ordinary multi-span continuous or simply supported bridges and all belonging to particular design era and all. So we are doing fragility by defining the particular bridge geometry and then doing. What about other bridges? We have to again rerun the simulation. Okay. So this is very computational expensive. So if you want to do a vulnerability assessment or loss assessment for a region, suppose for a state or for a region, for a class of a bridge, this kind of a method is very computationally expensive. Okay. So there is one more way we can do is that we can develop a multi-dimensional fragility curve. So instead, in our first case, our fragility curves are conditioned only on the ground motion intensity measure. Whether your demand is greater than capacity is conditioned only on your peak ground intensity or one ground motion parameter only. So we have to develop a parameterized seismic fragility curve. So let's see how to develop a multi-dimensional or parameterized seismic fragility curves, or we can call it a vector-based seismic fragility model. So you can see the models that we have developed earlier, where it gives the probability of failure, that is demand is greater than capacity, condition on a PGA. So this is very computationally expensive. We are doing only for one single bridge, and that's why it is being written. It is good for bridge specific seismic vulnerability assessment. We know the dimension of the bridge, we developed its seismic fragility curve. But what about other bridge? We know the deterioration condition, we develop fragility curves. What about the other deterioration condition? So what we can do is that we can develop the multi-dimension seismic fragility curves, where we are not conditioning our fragility. Now in this case it will multi-dimensional condition on different parameters like your ground motion intensity, and then we can condition different parameters like your geometric parameters, your modeling and structural parameters, and your deterioration parameter. If we develop such kinds of models, so what are the advantage of these? These are very flexible model and can be used for bridge specific fragility assessment. We can also, like if we have this kind of a surface or this kind of a models available for a class of a bridge, if we know the deterioration condition, we can just put into this equation, get the probability of failure for that particular deterioration case. We can also do a portfolio level seismic life cycle cost assessment method for the class of the bridge. So let's see how we develop. So what we are doing here, we are developing it for a set of bridge, for a class of a bridge. Like basically, suppose a multi-span continuous bridge having same kind of response, like in the sense, if you have a 3-span or a 2-span, different span length and all, like a column dimension along some 3 to 5 meters, 7 meter and all, not irregular. We can develop this kind of model to predict the vulnerability for a class of a bridge. Okay. Again, I'm saying there are some kind of limitation for this. We are only developing for a class of a bridge having similar, we can say, seismic response, how it behaves are same. Okay. So what are the different steps? First step is that we have to identify, like out of the different variables, the seismic response of a bridge depends on different parameters. Out of the different variables, what are the significant parameters? We should condition our fragility model on these parameters only. So this first step is basically identification of predictor variable and your screening design of experiment. Okay. So suppose this is my bridge, multi-span continuous bridge. We are taking the same bridge. So what are the parameters on which we can condition? You can be your modeling parameters, or like your abutment stiffness, your foundation stiffness, your material properties, and then we have your deterioration parameter, like how much is the average mass loss along the length of the rebar, how much is the cover concrete strength loss, how much is your anchor bolt diameter loss and all. So these are your deteriorated parameters. It can be also conditioned on your geometric parameters, means span length, your number of spans, your height of columns and all. And so in this work, what we have done is that we have identified, okay, the seismic response of the bridge components depends on, these are some of the parameters. So these are our initial parameters. We cannot develop a model which are conditioned on all these 19 parameters, because some parameters can be significant, some parameters can be insignificant. So what we do is that we do a screening design of experiment. A screening design of experiment is basically used in statistics and all, where we for this range of parameters we do initial simulations. Okay, initial simulation by setting the parameters at lower value, a mean value, and your upper value, and then do a range of simulation. First initial set of simulation, and then see the bridge response, like your peer response, your bearing response, your abutment response, and based on some of the statistical tests and all, we like Pareto charts and all, we see that which are more critical parameters that affect the seismic response of the bridge. Like for your column curvature ductility, the column curvature ductility depends obviously on the ground motion intensity. It depends on the how much is the area loss or the deterioration level, what is the span length of the bridge, how much, what is the yield strength of the reinforcement, the number of spans. So number we find from here the critical parameters for the column response. Similarly, we repeat from the same simulation, we take the results and then develop Pareto charts for different bridge component and try to see where it how much the seismic response depends on which parameter. So at the start, we started with the 19 parameters, and using screening design of experiments, we found that, okay, these are the red ones, which are the critical parameters on which our seismic response of the bridge depends. Okay. So once we find the critical parameters, we, in the next step, we do a modeling design of experiment. So what is modeling design of experiment? We have a set of parameters. We know its distribution or the lower limit and upper limit. We know the distribution. We again do a modeling design of experiment by using a statistical technique. We develop a combination of these parameters. Okay, in a simple word, if you want to say, we develop a combination of this parameter, and then for each row we develop the finite element model of the bridge. For each row of this parameter, we develop the finite element model of the bridge. So we have a range of bridge models, and then whatever the ground motion based on the site specific study and all, we randomly combine this ground motion with each bridge model, and then do a set of non-linear time history analysis. Again, here we are doing suppose 1000, or depending how we are statistically collecting the samples and all, we do the simulation and then do a non-linear time history analysis, and then note the response of each finite element simulation, like response of pier, abutment, and bearing for each finite element simulation. Once we have the finite element simulation response, like your output is again a vector, means suppose a pier response for 1000 simulation, there is a vector, and input is again 1000 into 10. So 10 predictor variable, 1000 into 10 matrix is there. Okay, so we have an input predictor variable, input predictor matrix, and we have an output. So output for different bridge component, like your column, bearings, and abutment. So we have a input and output, so we can fit a model on this. So again, in this work, what we have done is that we have used, instead of using the linear regression and all, we have used the advanced machine learning algorithms like your least square boosting and all, to try to fit a model on the bridge component response. Okay, so this is the thing that I was talking about, is basically written here, that we do a modeling design of experiment. Then for each row, we develop the bridge model and do a nonlinear time history analysis, and then output vector and your input matrix, we fit a model. We can fit a polynomial response surface model, or we can use advanced machine learning algorithm like ANN, least square boosting, your bagging, and all random forest and all. Here we have used the least square boosting, and then whatever the model we are predicting, again the concept of statistics comes in the picture. We are not fitting the model on all the response. We take 70%, 80% of the as a training data set, and then fit a model in this, and based on whatever is the model, we predict the 20%, and then based on the cross validation R-squared test and all, we see that, okay, whether my model is correct or not, whether it is predicting the response or not. Once we have this model ready, the next component, we have the demand model ready. So what we have now, your demand of your bridge component, suppose pier, as a function of ground motion intensity, bridge span length, bridge column height, or you can say your what is the deterioration level of the reinforcement, what is the abutment stiffness, what is the foundation stiffness. So we have a model. So if you put the point estimate of this model, we can get the bridge response. So basically, we are replacing your finite element simulation with a statistical model. Once we have the demand model ready, we can go ahead and then develop the component capacity models. So we can see it here, as I said earlier, either we can go to the experimental results and see the for similar kind of column whether this kind of experiments have been done or not, or we can validate our numerical model and then do a nonlinear static pushover analysis in the software, and then try to monitor the different qualitative description like yielding of reinforcement, spalling of concrete, your rebar buckling, or we can say the crushing of the core concrete. And then again, here we have to do again, as I said, we have to do a set of analysis to develop a model for that. So in this work, a response surface kind of model is basically developed to predict the different curvatures or for the different damage state, like your slight, moderate, extensive, and complete. Once we have this demand model and capacity model ready, a statistical model is there. We can compare it using logistic regression concept to develop a fragility models where your response or your probability of failure is conditioned on your intensity measure and your vector x. Here, vector x is basically your different parameters: bridge column length, bridge span length, number of span, or your what is the deterioration level and all. So if we have a similar kind of a bridge, if we just put these numbers into this equation, okay. So we have developed a parameterized or multi-dimensional fragility model. So if you put these numbers into this, we can get the fragility curves for different bridge components. Okay. Now, if we know that, okay, my bridge is getting deteriorated. So column which has suppose 1% reinforcement, which is with deterioration, it is going into suppose 0.8%. Like in terms of area loss, if you can say there is a 20% suppose area loss is there. If we just put into this equation, we can also get the aging bridge fragility curve. So you can see that this is my deterioration models available. What it says that at different times, what are the deterioration levels. So suppose at 75 years, my mass loss is of the reinforcement is 12%. The increase in coefficient of friction is 0.1 from 0.05. The anchor bolt diameter also gets reduced. Your corrosion of the steel plate of the bearings also gets reduced, and also we fit into these equations, then we get the aging bridge fragility curves also. So that's the advantage. We can also develop the seismic fragility surface. Okay, we fix all the parameters into point estimate and then vary two parameters like PGA and your span length. So you can see as the span length is increasing, the fragility is of the bridge basically increasing. So we can also develop the fragility surface. In addition to that, we can also see the median PGA for 50% of probability of failure, how it varies with the deterioration level and span length of the bridge. Again, these are the advantages of your multi-dimensional fragility surface for a class of a bridge. Like we can generate fragility surface by just putting into the statistical models that or the multi-dimensional fragility models that we have developed. So I'm again saying these are again developed for a class of a bridge. We cannot use this. Suppose I am developing only for a reinforced regular, ordinary, multi-span, simply supported or continuous bridge with steel bearing. This can be only used for this kind of bridges. We cannot say that this can be used for integral bridge or a multi-span simply supported bridge or not. So whatever we are developing, it is for a class of a bridge for a specific deterioration range of parameters. Okay. Now the advantage of this kind of a model, again, I'm saying these models are mostly used for a portfolio level loss assessment and all. We can do the seismic life cycle cost analysis using this model. Okay. So why this life cycle seismic loss assessment of highway bridges or the aging highway bridges are necessary? Look, as I said again, the motive behind doing this kind of work is basically to help the bridge owners or the stakeholders or the government to take some kind of proper decision in for the seismic retrofit of the bridge, whether to replace this bridge or retrofit for maintenance of this bridge and all. So if we give number in terms of metrics like monetary loss and all, so people can take decisions for the seismic law or for the retrofitting of the bridges and all. So traditionally in literature, again, what we do, we develop fragility curves for the bridge, convolve with the regional hazard curve. Hazard curve basically gives for the particular PG, what is the annual probability of failure. We get the annual risk. Then based on the repair strategy and cost, we develop the seismic life cycle cost. Now we cannot do it for a range of for all the bridges individually, do the nonlinear time history analysis, develop fragility curves, and then do the seismic life cycle cost assessment. So what we can do is that, again, we have developed a, suppose for a class of a bridge, multi-span continuous bridge, a simply supported bridge, we have developed the fragility surface model kind of this. Okay. So using this, suppose in this bridge network, I have this bridge, which is a 2-span bridge, 4-meter high, 19-meter column height. So what we can do, we can put into this equation the bridge parameters, deterioration parameters. Also, we can develop the bridge specific fragility curves, convolve with the hazard curve, get the expected seismic life cycle cost. So for bridge 1, we can get the expected seismic life cycle cost. Now, if you have another bridge, which is a span of 10-meter, column height of 3 meter. Remember here, this bridge is different, this bridge is different. So we can again use this equation, get the fragility curves, and then do the seismic life cycle cost analysis, get the bridge 2's expected losses, lifetime losses. Similarly, we can repeat for all the bridges in this road transportation system, which has a similar characteristic, and then do the portfolio level loss assessment. This kind of tools are basically useful for the governor or for the government and the bridge owners and stakeholders in taking decisions related to the retrofit and utilization of monetary resources. Okay, so this is something which I talk about about starting from the corrosion to the time-dependent seismic fragility assessment, and then I went through the parameterized seismic or the how we can develop multi-dimension seismic fragility model. Now, the last slide, little bit of all the summary of whatever I talked about. Like whenever we are doing vulnerability assessment for aging bridges, we have to basically consider the corrosion if it is located in harsh environmental exposure, and we have to model the bridge such that it can by taking uncertainty and also the improved deterioration model. We have to use, like in chloride environment, we cannot assume that uniform corrosion occurs. So we have to use improved corrosion deterioration model. And then we can also, obviously, when we are predicting the corrosion of the bridge, we have to do a probabilistic kind of a simulation by taking uncertainty of different parameters. And using this, we can develop time-dependent fragility curves. One more thing we can do is that, like for a loss assessment kind of some kind of a tool, we can, for a class of a bridge, we can develop multi-dimensional fragility models where your probability of failure is dependent on several parameters in addition to PGA, that is the ground motion intensity parameters, and your bridge geometric parameter, the deterioration parameter, and structural parameters. And we can develop a fragility surface using this. So the advantage of this that we can, based on the field instrumentation data or based on the geometric parameters of the bridge, we can predict its seismic fragility or the probability of failure. There is a significant reduction in the computational runtime, and these models can be also used for the prompt estimation of seismic life cycle cost assessment methodology. So these are some of the work I'm just trying to highlight it here. So I joined IIT Mandi in the last year. Before that, I was working at BITS Planning for 1 year and all. So my group in IIT Mandi specifically looks into the impact of climate change, how it affects the seismic vulnerability of highway bridges, the flood vulnerability, how climate change. We have seen in recent years, like in the last month or so, in the Himalayas or in the Himachal Pradesh, there is a due to climate change, there is an increase in the floods in the bridges and in the rivers that leads to the failure of the bridges and all. We are also looking into the resilience enhancement, like how to enhance the resilience of the existing bridges which are designed long time back. Like suppose for the older seismic provisions and all, which are designed with older seismic provision, how to retrofit these bridges, what are the probable retrofitting techniques and all, such that its lifetime resilience is basically enhanced and all. So I have few PhD students who are doing very good work along this line. So these are some of the things that I was talking about. I hope I did the justice with whatever the topic I have proposed. If there is any question, please feel free to ask.
So thank you so much for the lecture. So today we have seen about how corrosion is very important to a structure because it deteriorates the structure. And then we have seen the multi-stages, how corrosion can be divided, and how it is time to time, how it is going on developing in the structure. And we mainly discussed about how it is affecting the columns, which where we also follow the strong column and weak beam concept. So we think that columns are the very important topic to discuss, and we discussed about deterioration modeling and different fragile modelings, and we have also discussed about seismic modelings, and we have also touched upon very advanced topic as non-linear time history analysis and pushover curves. So yeah, now we can now I would like to request Dr. Praveen to read out the questions for Dr. Shivang. Over to you.
Thank you, Lakshmi. Thank you, Dr. Shivang, for giving a complete overview and the framework for the bridges and for the corrosion in detail. So we have number of questions. Let me start with the first question. One of the student has asked that what are the possible methods for protecting the steel reinforcement against corrosion?
Okay, so they're like durability, like durability, like if you read the textbooks of Professor Subramaniam and others, in the last there is a chapter on durability. Like basically we do not take into consideration these things during the construction. Like durability, the simplest thing is to increase the cover depth. Like if you see our IS 456 codes and all, we have seen that based on the exposure condition, like mild, severe, and extensive, they define different cover depth. Why we define different cover depth? Like for a structure which is located very close to the sea and all, very severe or extreme environmental exposure. So in that thing, we have to increase the cover depth. Once the cover depth is basically increased, then the delay, there is a delay in the initiation time of the reinforcement and all. So these are some of the simplest thing that we can do. Obviously, there are some different methods like zinc production and all, cathodic production of the protection of the reinforcement that basically delays the or doesn't leads to the corrosion of the reinforcement.
Okay, thank you.
So I will suggest that students to read the textbook on IS 456 codes and all the things are given there. The thing is that we do not read it. Yeah.
Right. And the follow-up question with respect to the cover reinforcement, which you have just talked about, what should be the clear cover around reinforcement, especially in bridges? Is there any specific requirement?
Yeah. So minimum for bridges, since it is located in extreme environmental condition, minimum this is 40 mm. Now, if you go towards our new code of IRC 112, our design of reinforced concrete now moves to limit state design. So again, in the IRC 112, there is a separate chapter on durability. There is separate provision on durability. So based on where your bridge is located, what cement content you can use, what water cement ratio, how much is the cover depth. So all these things are given there. So if you read our codes, everything's are there.
The next question is, it's basically an observation. During the corrosion, the reinforcement acts as anode, right? Is it possible by any method to make the reinforcement act as cathode so as to stop the corrosion process? Is it practically possible?
At the present moment, like if I guess properly, I have read something like this. Like there are some chemical or mechanical methods in which we can make the reinforcement in such a way that it doesn't lead to this anodic environment and all. So I am not yet at this moment like completely and like know where it is, but somewhere it is given, like this kind of things we can do it. Yeah, correct.
Thank you. And can we use some kind of fusion bonded epoxy coatings to prevent the corrosion?
Yes. Epoxy coated reinforcements are mostly used such that the reinforcements are basically the corrosion doesn't happen in the reinforcement.
So especially in the bridges, still people are going for the steel reinforcement, or can we use the fiber reinforcement also?
RP with that kind of reinforcement, epoxy coated reinforcement. If you see nowadays reinforcement which are getting the bridges which are getting constructed in Delhi and all, like I have noticed, like in some places they use this epoxy coated reinforcement and all. Yeah, I am talking whatever the corrosion. I am talking about the traditional approach that we use for the earlier bridges, where when we do not have this kind of enhanced or the improved durability provisions in the mentioned in the codes and all. So yeah.
So for usually about this fiber reinforcement, what is the range of strength we can expect compared to the conventional steel?
Yeah, these are again like they make mechanical properties in such a way that these are high yield strength reinforced deformed rebars only.
HYs, okay.
That number I cannot say at this moment, but this is just my whatever I have read. Like these are my
Okay. The next question is related to some finite element modeling. The question is, when you develop a finite element model out of the physical existing bridge, right? There is a model and then there is a prototype. What are the assumptions you make in order to develop the correct mathematical model which is close to the reality? Because there will be certain assumptions.
Exactly. Yeah. So again, that's why I said whenever we are developing, like suppose a bridge is there and we try to develop the model finite element model of that. Now this bridge experimental results are not available.
Right.
Obviously. So what we can do, we can go into the literature, like we have a huge database of experimental results are available. And thanks to people like you who are doing hard work in the lab to develop these experimental results, and also that people like me can validate our models. So like there are different database available. So if we for different bridge components, we can develop the model and then try to match with that experimental results. If you are closely matching, obviously one experimental result, not a set of experimental results we have to take, and then try to match our model, whether it is able to predict the response of that bridge component or not. So based on this step by step, and then once you develop the full scale bridge model, we can do this free vibration analysis or the modal analysis to see how the mode shapes are there. So from again, like we the first modes like for the bridges cannot be torsional mode shapes and all, and we can again go back to the literature and see like for this kind of bridge like multi-span simply supported bridge, what is the range of first fundamental time period is given and all. If our is coming along that range, that means that our model is more or less correct.
The next question is related to corrosion again. How do you fix the length of pitting corrosion in a steel bar? And how do you model in pitting corrosion bar in FEM software?
Yeah. Okay. As I said that this is again, this figure I will take it. So you can see
sure.
Like what the people have.
30 pages submit பண்ணா 60 pages எனக்கு வந்து submit பண்ணும். அப்பதான் வந்துட்டு கரெக்ட் பண்ணி delete பண்ணி கரெக்டா இருக்கும். நான் 60 pages comprehensive submit பண்ணேன். என்னால கரெக்ஷனே பண்ண முடியல, நிறைய எழுதி இருக்கா அப்படிங்கிறாங்க. நானே பண்றேன்.
Yes, can I proceed?
Yes, you can please proceed.
So
sorry for the disturbance.
Okay. So like this is my reinforcement. You can see that these pits are forming randomly across the length of the rebar. So we have what to model this, what we have done, we have gone through the experimental test results done by some certain researchers. What they did that they taken 100 mm reinforcement, then do the accelerated corrosion test, and then try to find the pitting factor. What is the pitting factor at different location? Okay. Now based on this, they give a distribution of the pitting factor. Okay. That distribution is a Gumbel distribution with a mean parameter and the shape parameters. And then what we can do is that we can model a one element, like we divide my bridge pier into 100 mm small elements. Okay. And for each 100 mm, we randomly pick a pitting factor and then assign to it. Then for the second 100 mm, we randomly pick the pitting factor and then assign to it. So in that sense, our results are closely matching with the like how from where we are taking the pitting factor.
Okay. The next question is for fragility analysis, from where I need to start reading as a beginner?
As a beginner, okay. Like there are several like kind of literature textbooks nowadays available from Springer and all, and then there are papers also. There are some of the papers that talks about the basics of seismic fragility analysis. Okay. There is a like if you can give the student my email ID. Like,
sure.
Feel free, like they can write to me. I will guide them.
Okay. The next question is, can we scale and consider only a few ground motions instead of considering the several ground motions?
Yeah. Again, so this is two different approach available in literature. One is cloud analysis, where we take a set of ground motion, and another one is incremental dynamic analysis, where we take a fewer ground motion and do a IDA kind of analysis. So there is a difference in opinion. Some people kind of like earlier days, nowadays people also do IDA analysis. But now what I feel like from my work is that since we have a large database of ground motion now available,
Okay.
because of the recording stations and all large database like from peer, in fact, from IIT Roorkee also they have recorded ground motion from India. So based on the regional seismicity, you can select a set of the ground motion, and then you can do an initial kind of a scaling, like in a sense, like if you matches with the design spectrum and all, some kind of scaling at the initial, and then do a cloud analysis. And suppose if you are very rigid with your ground motion selection in terms of very stringent, okay, these parameters only, then obviously you cannot go for a large number of ground motion. Then in that case, you can go for an IDA, incremental dynamic analysis. So more or less, like if you see the results, if you do a very good ground motion selection and all, the IDA result and your cloud analysis results mostly matches.
Okay.
Yeah.
The next question is how water cement ratio impacts the corrosion and how it impacts the initiation time of a corrosion.
Okay. The mostly water cement ratio, like kind of your diffusion coefficient, how much is the chloride diffusion coefficient, depends on the water cement ratio also. So higher the water cement ratio, the more is the chloride diffusion coefficient. So the higher the chloride diffusion coefficient, more is the corrosion initiation, more early is the corrosion initiation time. Now the rate of corrosion also depends on the water cement ratio. So people have given equation based on experimental tests that the higher the water cement ratio, the more is the corrosion rate for the concrete. Yeah.
Are there any design considerations that can minimize the risk of corrosion in new RC structures?
Yes, that's why I'm saying we have to do durability based design also. We have to consider durability provisions given in the code, do the construction properly, then our reinforced concrete structures will be safer. So our new code of IRC 112, there is a separate chapter given for the durability consideration for bridges. So whatever questions students have asked related to the cover depth and epoxy coated reinforcement, these all provisions are given in the code.
Okay. There is one question which you have already answered for this. Can you suggest some resources to learn about finite element modeling of bridges using open seas in detail? So I think they can write to you so
Yes,
that
please
if there is.
I will definitely help. Yeah.
Thank you, Dr. Shivang. And the next question: can we delay corrosion by applying an anti-corrosive coating chemical? Is it possible to delay the corrosion period?
Yes, there are some methods available. Like again, these are material aspects. Very advancements are there in the field of material engineering. So it's there. So I am again saying the same thing. Read the durability provision in IRC 112. Our IS 456 code is also new code I guess is coming. It is in the draft stage. I guess in that also more detail will be given. Right. If you look into bridges, IRC 112 durability chapter, read it.
And how corrosion impact the uncertainty of a model?
Yes, because we cannot predict the corrosion initiation time. We cannot say that the diffusion coefficient is always this fixed number.
A specific value.
Yeah. So experimental test says that like concrete strength is also not fixed. That's why we go to the FCK, not the mean. We developed a distribution. In a similar way, your corrosion parameters are also not uncertain.
And this question is related to the shape of a column. Does the shape of a column affects the corrosion?
Not that much, but
maybe he wanted to know related to the maybe the denser concrete. If we provide a denser concrete or if we increase the cover, maybe the corrosion process may be delayed.
Cover, then corrosion will get delayed.
Delayed.
Yeah.
As you have already mentioned that minimum requirement is around 40 mm, which one need to go for.
Yes.
And is there any type of physical test which you are performing to collect the input data before the modeling in finite element software?
Physical tests in the sense
maybe experimental test, because every detail cannot be get in the literature.
agree,
right?
agree. So like again, for my work, most of the thing I have taken from the literature. Like
Okay.
as I said, people have reported in the literature like, okay, concrete strain varies. If you have mean this much, if you can take as a standard deviation. Your reinforcement strength this much you can take as a standard deviation. So I basically goes towards that. For the modeling of the bridge component like abutment and all, again soil, it depends on what kind of soil it is. So soil is again uncertainty comes from there. So we take a range of parameters also there.
I have few more questions, but before going to that, I would like to ask in the audience if there is any question you can directly ask to Dr. Shivang. Anyone from the audience who wants to ask any question, or if you have any queries? And directly, if you want to ask, the floor is open. Okay. I'll ask the next question. Is the vulnerability curve and the fragility curve both are same or they are different?
They're different. They're different.
Okay.
Basically, we develop fragility curves that says how much the bridge is vulnerable.
Okay.
Vulnerability curves. Some people also say that cost also comes into the picture for developing vulnerability curve, but mostly we say as a fragility curves goes hand in hand and vulnerability curves. So we can say that fragility curves basically tells how much is my bridge is vulnerable.
So can I put in this way that the fragility curves basically gives you the probability, and the vulnerability curves gives you the loss. Can we say like this?
Yes, along that thing.
Okay. And how reliable this Monte Carlo simulation is?
Our Monte Carlo simulation basically we do if you do not know the fixed value. If you know that my concrete strength is always 25 MPa, we will not do a Monte Carlo simulation.
Right.
Yeah.
And which finite element software was used for the time history analysis, which you have shown? And also, where can we find the database of ground motion records for Indian seismicity?
So for finite element simulation, I have used OpenSeas.
OpenSeas
is a freely available software. And for Indian ground motion database, you can use PESMOS. PESMOS developed by IIT Roorkee. But again, as I said, it's in a like large, high recorded ground motion. You cannot get it from there. So based on the seismicity of your region, suppose you are doing for Bhuj region and all, you can based on the seismicity, what is the fault type, what is the characteristic of the ground. You can from the worldwide you can assemble these ground motion and then do the analysis.
Okay. And the last question of the day, what are some of the retrofit methods to improve seismic resilience of aging bridges, according to your viewpoint?
Yeah, so we are in a group, our group, one of my students is looking into that, like basically how FRP, fiber reinforced polymer, basically improve the resilience of the aging highway bridges. Okay, so like in the sense, if the bridge is already gets corroded, how if we do the FRP retrofitting of the corroded bridge only, how the performance of the bridge, the lifetime performance of the bridge based on resilience is improving, and the initial results shows that it's basically improved by 30 to 40% if the resilience of the bridge if you use FRP as a layer as a retrofit method.
Okay, thank you so much, Dr. Shivang, for addressing all the queries. And now it's over to Lakshmi.
Yes, sir. Thank you, sir. Now, I also want to thank all the participants for making this event a grand success. And I hope all the queries are clarified. And now I would like to call upon Ms. Minarvi to address the vote of thanks. Control to Minarvi.
So, good afternoon, everyone. My name is Minarvi Anupam, and I am pursuing MTech in Computer-Aided Structural Engineering at IIT Hyderabad. It's my privilege to propose the vote of thanks on behalf of IS Structure IIT Hyderabad Student Chapter for this occasion. First and foremost, I would like to thank our guest speaker, Dr. Shivang Shekhar, for sparing his time to grace today's webinar. Sir, I thank you for sharing your valuable knowledge on the topic Probabilistic Framework for Seismic Vulnerability Assessment of Aging Infrastructure System, which is of great interest to all structural engineering community. Sir, the insight we received today about the civil infrastructure systems such as RC structures, how corrosion deteriorates this structure, what are the various stages of corrosion and how it varies with time, what are the fundamental effects of corrosion and how they reduce cross-sectional area of the members. And yes, the case studies of bridges we saw along with the finite element modeling, and we went through a seismic fragility curve to determine the seismic performance of structure system. Thank you, sir, for sharing your knowledge on various topics. Now, I would like to express our heartfelt gratitude to our mentor, Dr. Praveen, for his valuable guidance and timely suggestions. My sincere thanks to Mr. Srikanth, our IT team, Ms. Babita, and Ms. Grace, our design team, for providing all the logistic support, help, and assistance. I would like to thank our program coordinator, Dr. Sunita Paliseri, for her continuous encouragement. I also thank all those who have directly or indirectly helped us to make this event successful. My special thanks to all the participants for their enormous cooperation. Last but not the least, I also want to acknowledge the effort, support, and cooperation of my entire team in making this webinar successful. Finally, I want to end this program by extending my sincere gratitude to all of you for being with us. It was indeed a great pleasure. So, this concludes today's webinar. Thank you all for attending. We hope you learned and enjoyed this webinar. Thank you.
And before we end, I would like to ask Dr. Subramaniam, sir, if you have any feedback, please, sir. We would like to hear from you. Sir, I think you are on mute. If you have any feedback or any suggestions,
Okay.
please. Yes, sir.
Of course, it's a highly mathematical subject, but I would like to appreciate Dr. Shivang for presenting it in a manner in which there is no mathematics involved in the presentation. That itself is a very great thing, because it involves a lot of parameters, lot of probability and other things, and unless you have a software, it is very difficult to explain things. But I think he made a very good presentation. Of course, many people might not know the intricacies of the subject, because it requires a lot of study, and also you should have some introduction on that subject. Otherwise, it is very difficult to understand each and everything which he is telling. So I appreciate Shivang once again for the excellent presentation.
Thank you, sir. Thank you so much.
Thank you, sir.
Because beautifully he has portrayed all the technical parameters into the graphical representation, so that one can easily connect. So that is the beauty of this presentation, and we really appreciate. Thank you. Thank you so much, Dr. Shiva.
Thank you, Praveen, for the invitation.
Most welcome. Most welcome. So
all the best.
Okay.
Thank you, sir.
Thank you, sir. So we conclude the session here, and next month we will be coming up with a new topic, and we will look forward to some more interesting sessions, as well as some exploration of the new knowledge on the recent developments in structural engineering. Thank you, everyone. Thank you for joining.
Thank you.